Hello everybody, and welcome back to another Big Ideas lesson. Today we're going to be talking about lesson 8.4. Now, before we jump into 8.4 notes, I want to talk a little bit about what we did in our lab earlier on this unit. If you don't know what I'm talking about, please go back to the 8.2 notes, and I believe in the description I left a link to this lab. The main thing is, we learned how to move our graph up and down, how to stretch it to be skinnier or how to shrink it to be wider. We learned how to flip our graph upside down, and we even learned how to move our graph to the left and right. What I've done here on this sheet of paper is I've taken our normal parabola and I've sort of graphed it out, nothing too crazy. And what we learned is, if you put your x in parentheses with something, something kind of magical happens. You may also notice that I've changed up my x values, and you'll see why in a second. So let's plug these in and figure out what the y values are. If x is 0, and I plug in 0 into our equation, we would get 0 minus 3 squared, which is negative 3 squared. And what's negative 3 times negative 3? Well, it's 9. So right off the bat, we're seeing a little bit of a difference. On this graph, x equals 0 gave you a value of 0. Here, it's giving us a value of 9. So that's going to be all the way up here. Let's see what happens as we continue. 1 minus 3 squared, well, that's just negative 2 squared, which is 4. So we'll get a value of 1, 4. Then, for 2, we would do 2 minus 3 squared. 2 minus 3 is negative 1. So negative 1 times negative 1 is 1. I'll fill in the rest of the values now. 3 minus 3 squared is 0 squared, so that's just 0. And 4 minus 3 squared is just 1 squared, which is 1. So as we look at what our graph looks like, we see a little bit of a change happen. Notice how, with the points I graphed, all I had was enough to make this little slant. It seems like our vertex is not going to be at 0, 0 anymore. In fact, where is this vertex? Well, it's all the way over here at 3, 0. That's interesting. So 3 really is the middle of our data set. So everything should be reflected over on the other side. If it looks like this all the way until it gets to 3, it should be the same on the opposite. So we should get a point around here, and we should see a point around here to make it perfectly flipped. This is our parabola of y equals x minus 3 squared. If you put a number, plus or minus, into parentheses, it'll move your graph to the left or to the right. But it's interesting. With a minus 3, you would normally expect that means left 3. I mean, that's where all of our negative numbers are, to the left. But it didn't move left 3, it moved right 3. This is something that's very fascinating that happens when we put our graphs into vertex form. X minus 3 squared will actually move your graph to the right 3. Well, if x minus 3 moves your graph to the right, what do you think maybe x plus 2 would do? X plus 2 squared. If you want to fill out a table, you can, but spoiler alert, x minus 3 moves to the right 3, x plus 2 will just move to the left 2. So this is what your graph is going to look like. After I plot all the points, it should look something more like this. This is y equals x plus 2 squared. So what's the deal with this? Why is it sort of flip-flopped? Why is it that plus 2 moves it to the left and minus 3 moves it to the right? Well, it has everything to do with what we call the vertex form of a parabola. Let's flip over to our notes on page 262. So, in the past, we have previously learned standard form of a parabola, or of a quadratic. Standard form is f of x equals ax squared plus bx plus c. And we want to recall exactly what each of these values do. I mean, our a value, for instance. We know that our a value is our stretch, our shrink, and our flip, right? And we recall that our c value moved our graph up/down. Technically, it just told us where the y-intercept is, but we can imagine it almost as if shifting our graph up and down. But if you remember 8.3, that simulation we did on Desmos, you'll recall the b value does some weird junk. It sort of bounced our graph up and down and left and right all over the place. In fact, if this was our starting parabola, the parabola sort of went down and to the left and then up and to the right and then down and to the right again. It just bounced around. So our b value kind of moves it to the left and right. Kinda left/right, but it doesn't do a very good job. Vertex form actually fixes this. Vertex form is another way of writing out the same equation, just rearranged so that it's much neater to use. The reason why we call it vertex form is, you'll see, the vertex is actually super, super easy to find in this form. Vertex form goes like this. F of x equals a times x minus h squared plus k. Now, right off the bat, we see some similarities and some differences. First thing is, our a value stuck around. Yay! Our a value did such a good job that it stays around here. It's still going to be our stretch, shrink, and flip. But we also see some changes. We still have plus something at the end, but we changed it. Before, we had our c value, which represented our y-intercept, and how much the graph moved up and down. We sort of gave it a promotion by turning it into k. Now, this is not going to represent our y-intercept up and down. The k value is actually going to represent the vertex up and down. So for instance, if we had plus 3 here, it means our vertex moves up 3. If we have minus 7, it means that it's going to move down 7. So this k value tells us how much up or down our vertex moves. But you may notice that our b value no longer exists. Instead, we have this weird h value. H is probably the most important part of this, because your h value tells you how much left or right your vertex moves. In fact, I'm going to call it the vertex right/left. This is key because it kind of matches what we saw before. You see, back in our example we did, our h value was 3. H equals 3. Because it's supposed to be x minus whatever your h is. So if we have x minus 3, it means our h must have been 3. That means it moves to the right 3. So based around what your h value is, if your h value is positive like it is here, again, that minus is supposed to be there, but the h itself is positive, then it moves to the right. But this problem did not have an x minus h. It had an x plus h. So what's the big idea? Well, anytime you see a plus sign, a plus is the same as minus a negative. So this really wasn't just x plus 2, it's x minus an h value of negative 2. All we did was we simplified it because minus and negative turns into a plus. So in this problem, our h value is negative 2. So it moves to the left 2. This is crucial. The h value tells you how much left or right you go. If the h itself, the number right here after the minus sign, is positive, that means it moves to the right. But if you see x plus something instead of x minus something, you know it's because your h value was a negative number, like it was here, and turned into x plus. Let me give you a brief example here. Let's say I gave you the following equation. I want you to tell me how this graph moved. If I gave you y equals 1/2 x minus 7 squared plus 6, could you tell me what the vertex is? Well, if our h value controls how much left and right our vertex moves, or right and left I should say, and our k value controls how much up or down we move, we know that our vertex is just going to be h, comma, k. So what's our h value here? X minus h is the formula. Instead of an h, we have a 7. So our h value here equals 7. And what's our k value? Well, it's plus k, and here we have plus 6, so our k value is 6. That means our vertex is at 7, comma 6. This is what I meant when I said it's much easier to find the vertex in vertex form. You just got to pick out your h and pick out your k. Let's flip over to page 264, actually. We're skipping 263. Here's what I want you to do. I want you to find not only the vertex for both of these, but I also want you to find the AOS, the axis of symmetry. We remember a fun fact about the axis of symmetry and the vertex. The axis of symmetry is equal to the x value of your vertex. Try these two problems out. Pause here and try out problems 7 and 8. Find your h and k to get your vertex. Use the x value of your vertex to find your axis of symmetry. Pause here and let's see how we do. So, to find the vertex, let's start off by remembering that our vertex is just going to be h comma k. Well, what's our h value here? We have x minus 1, and we know that we're supposed to have x minus h in parentheses. So we know our k value must be 1. That also means our axis of symmetry is x equals 1, because they're the same. Our k value is what comes afterwards, because it's always x minus h squared plus k. So what's our k value here? Our k value is 4, so our vertex is at 1, comma 4. Things get a little bit crazier over in number 8, though. Because we don't have x minus h, we have x plus 1. How can we turn x plus 1 into x minus something? Well, the only way this works is if our h value is negative. The only way this works is if our h value is negative, because two negatives make a plus. And since we made plus 1, it makes sense that our h value must be negative 1. Our h value here is negative 1. Again, anytime you have a plus sign, it means your h value is negative. So our k value is a little easier to find. It's just going to be the number that comes afterwards. So that's negative 5. And of course, our axis of symmetry is equal to the x value of our vertex. Very nice. That's it, actually, for 8.4, where we learned about vertex form. For extra practice, try out the Big Ideas assignment and see how you do. But with that said, everybody, have a fantastic rest of your day.